Okay, now let's study this circuit and see how it works. So of course, as I said, usually we need to draw this load line, and we need to find the relation between VCE and IC, and then draw this load line, and then find VCE and IC. This is what we need to do. Okay, there are two methods here to solve this circuit. One is approximate, and one is almost exact. Yeah, you can also have exact solution, but believe me, the difference is not much. Let us see first the approximate solution. How can we do that? First here, as I said, this high stability, as we have one only DC source. VCC is almost what here? The voltage, this VCC is equivalent to VCC plus VE in the previous circuit. Because in the other one we have positive and negative. Here we have positive and ground. Then VCC is equivalent to VCC plus VE. Okay, what is the relation between VCE and IC? This current and VCE is a voltage here. This is a voltage. It's very clear that this voltage equal what? Equal the voltage VCC, the source, minus this voltage and this voltage. The voltage dropped on RC and the voltage dropped on RE. Then you can say that VCE equal VCC minus the current here is IC times RC, and the current here is approximately IC times RE. Then you can say that this is VCE equal VCC minus IC between bracket RE plus RC. So this is the relation here that is used to draw the load line. So if you want to draw the load line here, if VCE is 0, then IC equal what? Equal VCC divided by RC plus RE. This is the saturation current. What about if IC equals 0, then VCE and VCC are the same. So here is the cutoff voltage. Then if you know these two voltages, these 2 points, then you can draw the load line, and you know that the operating point will be on this line, Then how can we decide where is this point? First, we need to calculate IC, then we need to calculate VCQ. The question is now, how we calculate IC and how we calculate VCQ? Okay. As I said, there's a solution that's approximate here, which is easy, and there's one that's a little bit it's not difficult, but this one is easier. So first, if we assume that the current here is negligible here, this one is IP, and we know that IP is very small, so we can neglect it. So if I assume that we have a current here, the current here, we approximately it will continue in R2. So as if this one doesn't have any current. So in this case, the voltage at this point is the voltage divider here, equal VCC time R2 over R1 plus R2. Okay, so VB, this point, the voltage here at this point, equal what? Equal VCC, this is the total voltage, multiplied by R2 over R1 plus R2, which is this relation here. So this is the voltage VB. So now if I know the voltage here, okay, then the voltage at this point is what? Is this VB minus 0.7, minus 0.7. This is the voltage at this point here. Okay. Now if you divide this voltage over RE, this will give you IC. Or IE, of course, but approximately it will be IC. As I said, IC and IE are almost the same. So IC will be what here? Will be approximately VB minus 0.7 divided by RE. So this is the approximation. Okay. Then after that, we need to find VC using this relation here. We know this relation. Just find IC and then substitute by the value of IC to find VCE. So this is a very simple way to do it. Okay, to use this voltage divider first, and then to calculate IC, and then after that you calculate VCE. The second method here is you can say, oh no, there is a current here. So these two are not in series, then you cannot say voltage divider. Then how we solve this one here? We need to okay, this is we have already solved this one here, but okay, but we're still in the approximate solution. Okay, so here, as there's nothing new in this part here, But you notice here that IC and VCE are not function of beta at all. So in this case, you have very stable system here because beta, IC and VCE are not a function of beta. But you know that this is approximation. It is still a function of beta. So let us see the one that's more accurate than this one. To solve it, then in this case you can say, okay, no, we have a current here, we cannot neglect it, even if it is very small, but it's okay, let's consider it. So how we do this, we need to find the Thevenin equivalent circuit between P and the ground, between this point and the ground. We need to find the Thevenin equivalent circuit. We have to return back to circuit theory. Okay, so we need to find V Thevenin and R Thevenin. V Thevenin, in this case, will be the voltage divider. In this case, will be R2 divided by R1 plus R2 times VCC. Okay, this is V Thevenin. VCC times R2 over R1 plus R2. This is the V Thevenin. Is not VB. Remember here. Okay, and R Thevenin equal what? For R Thevenin, you have to short the source. So this source here will be short. This means that it is ground. Will connect to the ground. Okay, so in this case, R1 and R2 will be parallel to each other because this one will be connected to the ground because we short the source. Then R1 and R2 will be parallel to each other. Okay, then R Thevenin will be R1 parallel with R2. Parallel with R2. Okay, so this is the Thevenin equivalent circuit, this part here. So connected here, okay, for this part, then this is the Thevenin equivalent circuit, V Thevenin and R Thevenin. Now when you look at this circuit, and if I want to calculate IC, how do I calculate IC? I have to use this loop. This voltage is dropped over R Thevenin, and this part here, VPE, and this resistor. So we have three parts here. So V Thevenin equal what? Equal this current time R Thevenin, which is IP time R Thevenin, and plus VPE plus RE times the current here. The current here is approximately IC. Okay, so we know that IC, then we have IC and IP in this equation. IC and IP in this equation. But we know that IP equal IC divided by beta. Then in this case, here is the equation. Then we can replace this IP by what? By IC divided by beta. Then in this case, you have one equation in one unknown, which is IC. Okay, then you can calculate IC. After that, you use the same equation to calculate VCE because you still use this loop here, this one here, this branch. So VCC equal what? Equal RC times IC plus RE times IC plus VCE. Okay, or you can merge them together. Then you can say VCE equal VCC minus IC times RE plus RC. Okay. Then in this case, we have to, the step for the solution is first to find V Thevenin, as I said, voltage divider, and then R Thevenin, R1 parallel with R2, and then you draw this line exactly the same like in the first method, and then calculate IC using this equation. Now I got this equation from the Thevenin equivalent here, from this loop, from this equation. So here IP is IC over Q. Then you just take IC outside and then put everything in the other side. Then you will get IC equal this number here. Okay, V Thevenin minus VBE, which is 0.7 volt, divided by RE plus R Thevenin divided by beta. Okay, so now, and after that you substitute in this equation to calculate VCE. Now, what do you notice here? Where is beta? Beta is here. Okay, so beta is here. So when beta is here, do you think that when you change beta, this will change IC? For sure, it will change IC. For sure. Okay, so how much, for example, it will change IC? If this RE is much larger than R7 over RP over beta, then the change here will not affect too much. Assume that this is 1000 and this is 1, for example. So if this is 1000 and this one become 2, for example, or become 3, this will not change a lot. Okay, and now let's see, R7 you divide it by beta, and usually beta is 100, 200, something like this, big number. Then this is very small with respect to RE. That's why the effect of beta is very small. Okay, and we will see how it is stable, but we have to use this method here because in the approximate method there's no beta, so you do not have any the IC and VCE are not function of beta at all. So you do not have, you have a perfect solution, but of course this approximation, as I said. So let us solve problems using the approximate or the exact solution here. This one is the exact solution, and then after that we'll see the approximate. So here beta equal to 100. Okay, and I have this problem. So what are the steps? The first step is to calculate V7. V7 equal 15 volt time 4.7 divided by the total resistance here, which is 4.7 plus 10. Okay, then this is V7. Let's calculate it and see if we have the same answer or not. 15 time 4.7 divided by the total resistance, which is 10 plus 4.7, which is 14.7. That is 4.796 volt. That's right. Okay, and then you need to find R7, and R7 equal what? Equal 10 parallel with 4.7. Then you multiply them, 10 times 4.7, and you divide over the summation, which is 14.7. That's 3.197, which is almost 3.2K. So now we have V7, we have R7. Okay, and then we draw the line. This is the load line. Here, the cutoff voltage is VCC, which is 15 volt. This 15 volt. And the saturation current here is VCC, which is 15, divided by this resistance here, the total resistance, 3.3 plus 3.29, which is 7.2. Okay, so now it is 15 divided by 7.2, that is 2.08 milliampere. Okay, so this is the saturation current. Now, next step is to calculate the actual current here, IC. How do you get as the actual current? You have to return back to this equation. It's the same equation here, this equation. Okay. So V7 equal what? Equal 4.796. Let's calculate it. I calculate the current here. IC equal V7, which is 4.796 minus PBE is 0.7 volt. You divide it by, you open bracket because you have different items here. RE equal 3.3K plus R7 is 3.2K. Okay, and you divide it by beta, which is 200, and you close a bracket, and then equal is 1.235 milliampere. Then this is the current IC. Then you substitute by this current in this equation to calculate VCE, multiplied by RE plus RC. So you multiply this by time 3.3 plus 3.29 is 7.2. So multiply by 7.2 equal. Okay, and you give it a negative sign, and you add VCC, which is 15. Then the voltage now is 6.1 volt. This is VCE. Okay, so this is the solution for with this almost exact solution here. Okay, let us see if we solve it using the approximate solution. The approximate solution, and we have all the formulas here. Okay, so how we do that? First, we need to calculate VB using voltage divider. That will be VCC time this voltage here time 4.7 divided by 4.7 times 10 plus 10, which is 4.796. This is similar to V7 on the previous slide. Okay, so this is VB. Okay, if you want to draw the load line, will be the same. There's no difference in the load line. There's no problem in the load line. The same. Okay, but now let's calculate IC and VCE. IC equal what? Equal the voltage here is VB, which is this voltage. This voltage is here. Okay, and you the voltage in this point here at this point is 4.796 minus 0.7 volt. This is the voltage here. Okay, so if you want to calculate IC, okay, it is this voltage divided by 3.3k. You divide it by 3.3k, then this will be the current here, 1.241 milliampere. The solution in the previous slide was 1.235 milliampere. You see that they are very close to each other. And then you substitute in this equation to calculate the voltage. IC is 1.241. You multiply it by RE plus RC, which is 7.2 kilo ohm. You give it a negative sign, and you add VCC, which is 15 volt, equal 6.06 volt. 6.06 volt. Okay. You see the difference is not huge here. 6.06 and 6.1 volt. There's no big difference. I believe the next slide is to study the stability, and when we study the stability, we have to use the exact number 1.235 and 6.1. So let us use this Thevenin equivalent when beta, for example, equal 100, and see what is the difference here, how IC and VCE change. So if beta is 100, we still have the same load line, okay, but what about IC? IC in this case equal V Thevenin, in this case is the same, 4.796, okay, minus VB, which is 0.7 volt, okay, divided by, open bracket, RE, which is 3.3K, plus R7, which is 3.2, divided by beta, which is 100. Close it, and then open this equal 1.229 milliampere. So this is the current when you change beta from 200 to 100, from 200 to 100. You see the difference? What's the difference here? Nothing here. When you subtract, just subtract minus 1.235. It is 0.0057. Very small number. Very small error here. Okay. Now, if we want to calculate VCE, we have to substitute by this value in this equation. Then we have 1.229 times RE plus RC is 7.2K. Okay, and they give it a negative sign, and then you add 15 volt. Then the result is 6.15 volt. And when beta equal 200, it was 6.1 volt. So this the difference is 0.05. There's no big difference here. There's no big difference. So the difference is 0.05. If you want to calculate the percentage change, you divide it by the original value of 6.1, and you multiply this by 100. So it is actually 0.81 or 0.82%, even less than 1% change. Okay, so here the difference is 0.05. You divide it by the original value, which is 6.1, and multiplied by 100. This will give you the percentage change, which is 0.82%, less than 1%. Okay, when you use this method here. Let us see another method. Okay,